If you're an engineer working with pressurized equipment, you've definitely heard the term fitness for service. It's not just some industry jargon, it's an absolutely critical framework we use to keep our most important assets running safely. So let's break down exactly how it works.
Okay, so picture this. An inspector hands you a report. This shows metal loss, maybe a dent, or even worse, a crack. And suddenly, all eyes are on you. Operations is pushing to keep things online, but you know that safety is the bottom line. So what's the call? This is the exact moment where having a structured approach isn't just nice, it's essential. And that structured approach is fitness for service, or FFS as we all call it. Think of it as a formal engineering evaluation, spelled out in standards like API 579. It's what takes the guesswork and the gut feelings out of the equation. It lets us go from staring at a flaw with a lot of uncertainty to having a real technical basis for making a sound decision.
Now here's what you've really got to understand. FFS isn't some single magic formula you just plug numbers into. The best way to think about it, and how I always explain it, is that it's a specialized toolkit. You know, a mechanic has different wrenches for different bolts, right? Well, an integrity engineer has different FFS tools for different kinds of problems.
And this toolkit is neatly organized into 3 distinct levels of assessment. Each one offers a different level of detail and precision, and each is designed for the specific situations you're going to face out in the field.
The whole framework builds on itself, which is what makes it so smart. You always start with level 1, the screening assessment. If that doesn't give you a clear answer, you can step it up to level 2. And for the really tough nuts to crack, you have level 3. It's a logical, efficient progression.
Level 1 is your first line of defense. It's like a quick go/no-go check. It uses really simple formulas and, this is key, it's built on very conservative assumptions. The goal here is speed. You want to quickly screen out things that are obviously fine, or just as importantly, flag the ones that definitely need a closer look.
So let's make this real. An inspection report comes back saying a vessel shell that started at 25 millimeters is now down to 18 millimeters in one spot because of corrosion. A level 1 assessment is basically a direct, simple calculation. Does that leftover 18 millimeters still meet the minimum thickness required by the code, plus any safety factor? It's a clean, straightforward check, pass or fail.
But what if your level 1 check fails? Or what if the problem isn't just simple thinning, but a crack? Well, that's when you reach into the toolkit and pull out the next tool, the level 2 assessment. Now we're getting much more detailed. We're moving past those broad assumptions and actually modeling the specific shape and size of the flaw. We start bringing in more advanced tools like stress analysis and fracture mechanics to really understand how that specific flaw is going to behave.
And then, for the most challenging cases, we have level 3. This is the top-tier specialist tool. You save this for when the component shape is really complex, the operating conditions are unusual, or when levels 1 and 2 just aren't giving you a clear answer. Here, you're firing up powerful software to do something called finite element analysis, or FEA, to build a super detailed computer model and see exactly how it will perform.
So, with these 3 tools sitting there in the kit, how do you know which one to grab? Well, that choice really comes down to a trade-off. It's a balance between how complex the problem is, what kind of data you actually have, and frankly, how much time and resources you have.
This little table lays it out perfectly. Level 1 is low complexity. You just need basic data, like a thickness reading. It's for that initial screening. Level 2 gets more complex and you need more detailed data, like the exact size of a flaw. Level 3? That's high complexity and it demands extensive data, sometimes even new material tests. Picking the right level from the start is what makes for an efficient assessment.
Okay, this is probably the most important point I'm going to make. After all the number crunching is done, what happens next? It is absolutely crucial to remember that the FFS assessment is not the decision. It's the technical input to the decision.
Getting a pass on an FFS assessment is not a free ticket to just keep running that equipment forever and forget the flaw even exists. No way. All it means is that you have technical proof that, under the conditions you analyzed, the component is currently fit for service. The final call? That requires a much bigger picture.
The FFS result is just one piece of a much larger puzzle. As the engineer making the call, you have to weigh that result against everything else you see here: the real-world costs, the consequence of failure, what happens if it does break, how much longer it's expected to last, and of course, all the regulatory rules you have to follow. It's a true exercise in engineering judgment.
Now, before we finish up, there is one last thing. It's the foundation that this entire FFS framework is built on. And if that foundation is shaky, the whole thing can come crashing down. I'm talking about data quality.
I honestly cannot say this enough. Every single FFS assessment, from the simplest Level 1 check to the most complex Level 3 FEA model, is completely and totally dependent on the quality of the inspection data you start with. It is the absolute classic case of garbage in, garbage out.
And in our line of work, misleading results isn't just some academic problem. It can be incredibly dangerous. An assessment that's based on bad data can give you a completely false sense of security, and that can have catastrophic consequences. The integrity of your final decision starts with the integrity of your initial data.
This means your thickness readings have to be precise, your crack sizing has to be accurate, your overall mapping of the damage needs to be reliable. The trust you put in your NDE team and their techniques, well, that's absolutely paramount to doing a valid FFS assessment.
So as we wrap this up, I want to leave you with this final thought. Before you even start a fitness for service assessment on a piece of equipment, you need to first ask yourself a different question. You need to do an FFS on your data itself. Is the information you're holding in your hands truly fit to be the foundation for such a critical safety decision?